Absolute value function is a function that has a variable within an absolute value symbol. And the symbol is drawn like two bars and the absolute value written inside. So we're going to look at the first absolute value function, y equals the absolute value of x. This is known as the parent graph. And we're going to graph the function by making a table of values. We're going to use negative 2, negative 1, 0, 1, and 2. When we plug negative 2 into y equals the absolute value of x, the answer will be 2. When we plug in a negative 1, we will get 1. 0 will give us 0. And if we substitute in a 1, we will also get 1. And when we substitute 2, we'll get 2. So if we were to graph that on the graph, 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 1. And when we connect that, our graph will take on a V shape. So this graph of a y equals absolute value of x is known as the parent graph. And you'll notice that it resembles the letter V. If you had to guess where the vertex of the parent graph is, we do it, and it's actually 0, 0. Now we're going to look at a second example. We graph the equation y equals the absolute value of 3 minus x plus 2. So the first thing we're going to do is find the vertex. For the x-coordinate of the vertex, we take the expression inside the absolute value bars, so that's right there, and we're going to set it equal to 0. If we do 3 minus x equals 0, we know that x is equal to 3. I'm going to fill that in right here, and now I'm going to look for the y-coordinate. The y-coordinate is whatever is outside of the absolute value. So if we look on the outside of the absolute value, we see a plus 2 here, so my y-coordinate is 2. So the vertex of this function would be 3, 2, and as an ordered pair. So I'm going to plot that on the graph, 3, 2. So now I'm going to make a table of values now that I know my vertex. So I'm going to put your vertex in the middle of your table of values, and we're going to pick points that are just to either side of it. So I'm going to pick 2 and 1 and 4 and 5. So when I substitute those numbers into y equals 3 minus x plus 2, the x in I will get 4. When I plug the 2 in, I'll get a 3. We already know the vertex. When I plug a 4 in, I will get a 3. And when I plug a 5 in, I will get a 4. And if you notice the pattern here, that's actually supposed to happen. Okay? If you plot points away on either side of your vertex, you will sort of see like a mirror pattern. I'm going to plot those points. 1, 4 is right here. 2, 3, 4, 3, and then 5, 4. And of course, that takes the shape of a V. So that's a good way to check yourself. If your graph does not look like a V, something went wrong, either in your math or in your plotting of the points. If we want to talk about the domain and the range of this function here, domain, remember, is the possibility of your x values. So what can your x values be? If you look along, they can be anything along the x-axis there. So it will be written as negative infinity to infinity. If we look at the range of values, notice that our graph does not exist below a y value of 2. So our 2 is our lower end, and then it goes up to positive infinity. So 2 things you should note on the bottom, some good tips. The first one is to put the vertex in the middle of the table. And another one is to choose x values on either side of the vertex. Now we're going to practice doing some graphs by first finding the vertex and then making a table of values. So remember, your vertex, your x value will be inside the absolute value. And then your y value will be out. So if we look inside here, if we were to solve for x, we would get a 3. Okay, and then our y value is just what we see out there, 5. So that's my vertex. And remember, we talked about putting it right in the middle of the table of values. So I'm going to choose just above and just below. And those will be the values that I fill in to find my y values. So for the first one, if we substitute 1, it will be minus 3 minus 3. And then 1 minus 3 is a negative 2, but because of the absolute value bars, we know we get 2 minus 3, negative 1, which is positive 1 because of the absolute value, and we end up with a negative 4. We come down here, 4 minus 3, absolute value minus 5. 4 minus 3 is 1 minus 5, negative 4. And if we put a 5 in, 5 minus 3 minus 5, that's 2 minus 5, negative 3. So we notice the symmetry here, so we're probably in pretty good shape. Let's plot our points. 1, negative 3 is down here. 2, negative 4 right there. 3, negative 5 is right here. 4, negative 4. 1, 2, 3, 4 right here. And 5, negative 3 is right there. So that graph will look like this. And we talk about domain. It'll be negative infinity to positive infinity. Okay. And our range, it doesn't go past negative 5. Then it goes infinitely up. Notice number 2 is a little different because of the 2 out here. And this we kind of look at it as if it was like a slope. Okay. And that's going to stretch the graph. And it's also going to give it a more narrow V shape. We try to figure out our graph. We look inside the absolute value. And if we set that equal to 0, it would be negative 4. Or if we just look at it and use the opposite, negative 4. And then the y value is always down there, negative 1. So negative 1 will go inside my table, right in the middle there. And I'll go 5, negative 6 direction, 3, negative 2 in this direction. So if we put 2 times negative 6 plus 4 minus 1, we have 2 times the absolute value of negative 2 minus 1 equals 2 times regular 2, right? Absolute value of negative 2 is positive 2 minus 1. So that's 4 minus 1 or 3. If we plug negative 5 in there, 2 absolute value of negative 5 plus 4 minus 1 equals 2 times the absolute value of 1 minus 1, which would be 2 times 1 minus 1, which would give me 1. Okay. Then if we plug in negative 3, 2 times the absolute value of negative 3 plus 4 minus 1 equals 2 times the absolute value of 1 minus 1, which is just minus 1 or 1. And the last one is 2, negative 2 plus 4 absolute value minus 1 equals 2 times the absolute value of negative 2 minus 1, which simplifies 3 times 2 minus 1, which gives us a 3. And if we check out, we see the symmetry here, so we know we're probably in good shape. So now let's plot it. Negative 4, 1, 2, 3, 4, negative 1 is right there. Negative 5, 1. And negative 6, oops, 5, 1 is right here. Negative 6, 3 is right here. Let me erase that mistake there. There we go. And then on the other side, we have negative 3, 1 and negative 2, 3. So if we notice our points are stretched a little more, they're not just up 1 over 1, they are stretched a little bit. And that's what our graph looks like. And if we are write our domain, again, it's all reals, negative infinity to positive infinity. Our range goes no lower than negative 1, and it goes up to infinity. Okay, try number 3 and 4 and pause the video, and then I'm going to record again, and you can check your answers. Okay, so if we were to use the vertex negative 1, 2, and use the table of values as our x values, negative 3, negative 2, negative 1, 0, and 1. When you work things out, you should have gotten 3, 2.5, and then another 2.5, and it's 3. Remember, these are symmetric, so it should work out that way. Okay. If we were to graph that, we get negative 3, 3, negative 2, 2.5, negative 1, 2, and then we have 0, 2.5, and 1, 3. Okay, so that kind of flattens out the graph. Notice it opens wider. Okay, and that's what that 1/2 outside in front, that's like a slope of 1/2. Okay, it flattens the graph and makes it wider. So the domain for this is all reals, negative infinity to positive infinity. My range is at 2 going up to infinity. Okay, now try number 4. Keep attention on the negative side right outside here. Okay, that's going to do something to the graph. Think about what that does to your quadratic graph when you're doing this. Okay, so that negative number out there is going to flip the graph just like it does for a quadratic. The vertex is 4, 3, so I put that in my table of values, and when I solve, when I plug in 2, I should get a 1. When I plug in 3, I should get a 2. When I plug in 5, I should get a 2, and when I plug in 6, I should get a 1. Okay, so if we plot those points, I'm starting my vertex 4, 1, 2, 3, 4, up 3. Okay, and then we're going to go 3, 2, and 2, 1. And then on the other side, we're going to go 5, 2, and 6, 1. If you notice, the graph is flipped upside down. So now this will have an effect on your domain and range, not so much on your domain. That'll be negative infinity to positive infinity. But when you're looking at your range, you're coming up from negative infinity, and then you're stopping at, what is that, 1 at 3.